molecular spectroscopy. In this session today, I will take up the basic aspects of instruments used for spectroscopic measurements, and typically we are going to talk about molecular spectroscopy. The today's session has been planned as follows. To begin with, I will try to review what we did in the previous sessions. Thereafter, we will try to understand that what are the essential components of instruments used for making spectroscopic measurements. And in this context, we will try to study in slight details about the radiation sources used for different types of spectroscopical studies. Thereafter, we will come to monochromators or some kind of devices which are used for selecting the wavelengths out of the polychromatic sources of radiation. And thereafter, we will talk about what are the different types of sampling devices used to make this study possible, because this will depend on the kind of radiation I am going to use, and towards the end we will try to sum up what we do today in this session. Let us make a beginning. Let us make a beginning by recalling what we did earlier. What we did earlier is that we started with defining spectroscopy and outlined its scope and significance. Thereafter, we discussed the nature and characteristics of electromagnetic radiation. This was followed by recalling the nature of atoms and molecules in terms of the energy level diagrams and quantization and things like that. Thereafter, we explained the types of interactions involved between EM radiation and matter. That is basically what spectroscopy is all about. This was followed by outlining the necessary conditions for the interaction between radiation and matter to take place. That means, what are the kind of prerequisites involved. And thereafter, we discussed the types and characteristics of a spectrum, that is absorption spectrum, emission spectrum and things like that, and then the characteristics like position, width and intensity, etc. And now, let us try to raise a question. Okay, fine, we said spectroscopy is interaction of radiation and matter, and then there are different types of interactions possible, different requirements are there, but how do we actually make a measurement? So, that is a question we want to raise today. And we know that for any measurement of this kind, we need some kind of a device or an instrument. Okay. So, we will be needing some kind of an instrument to make a spectroscopic measurement. That means, if I want to study the interaction of radiation and matter, irrespective of which region I am talking about, I have to have some instrument. I am talking about a broad term as an instrument. Now, let us try to have a look at what are the essential components of any instrument for spectroscopic measurements. We need to have, before I proceed further, let me recall that we have talked about spectroscopy as study of interaction of radiation and matter, and the radiation in different regions of electromagnetic spectrum interacts with matter. So, that is the bottom line with us. Okay. So, for that to be studied, we need to have, the first thing is you have to have a source of radiation. Thereafter, since I am going to use different regions of the spectrum, so I should have some means of selecting the appropriate wavelength out of that region, out of the whole source. Thereafter, I should have something to hold my sample which I want to study. That means, I have to hold matter, atom or a molecule or other things like that. I have to have some kind of a device to hold my sample over there. And then, when the radiation and matter interact, something happens as a consequence of that, whether the radiation is absorbed or emitted, or there is some kind of a scattering has taken place. So, we need to have some device to measure what has happened as a consequence of that. Okay. So, need some kind of a detector for the radiation which is coming after the interaction has taken place. And lastly, we need some kind of a mechanism, some kind of a device which will process this data and give us some kind of an output in terms of a spectrum. So, that is the bottom line, that is the broad outline of what are essential components of a instrument. Let us talk about each one of them one by one. Let me just give you a small general outlay. That means, what you have is, as I just mentioned, we have to have a source, and then the source is typically a polychromatic source. That means, radiations of different wavelengths are coming simultaneously from the source. Then, since I want to talk about the interaction of radiation of a given type or maybe of a given wavelength with the matter, so I want to do some kind of a spectrum. You remember that spectrum essentially is a spread of interaction of different wavelengths or frequencies. So, I need a device which is going to monochromatize that, give me radiations of, say, if I have say a visible lamp. So, that gives me radiation right from about 370 nanometers to 760 nanometers. but I can't put all the radiations onto my matter and see what happening. It will be quite a complicated outcome. So, what do I do instead is I use some kind of a device like a monochromator, which will give me wavelengths of say 370, 371, 372. So, I can tailor my input here. That means, I can use a device which can give me radiations of one particular wavelength at a time. Thereafter, I make this radiation pass through the sample and see what happens over there, whether it is absorbed or not absorbed, if absorbed to what extent. So, that I measure with the help of a detector, and then the output of the detector goes to some kind of a device which gives me an output, a spectrum. Okay. So, that is the general layout of the essential components which we use in a spectrum measurement. Now, as I mentioned earlier, let me now take up one by one the different components. The first one is the radiation sources. As we remember that our EM spectrum is very broad. It starts one end is over gamma rays, another end you are going to have radio waves and things like that. So, there is a whole range. So, there can't be any one source which gives you all radiations. So, we have to have different kind of sources for different regions of the spectrum I am talking about. Say for example, if I want to talk about if I want to study rotation spectrum, so I need radiation in the microwave region. So, what do? I will use some kind of a device called as klystron valve. So, that is actually a device which gives you the radiation which are in the microwave region. Similar device is used in our microwave ovens which we use at home. And then if we move further, suppose I want to talk, I want to study interaction in the IR region. So, for IR region, what do we have is typically what we do, we take some kind of inert solid and heat it electrically, and that hot solid gives out radiations which fall in the IR region. Okay. And the common examples here are, one is a Nernst filament, wherein we take some kind of a rare earth oxide and then heat it electrically, and that gives an output which is in the IR range. Or another example could be Glauber filament, wherein we take a rod of carborundum and heat it electrically to get output in the infrared region. Now, if I want to study Raman spectroscopy, basically for Raman spectroscopy, typically conventionally mercury arc lamps are used as a source of radiation, but nowadays most of the instruments employ lasers because they are preferred sources, because laser sources are very intense. You remember that the Raman spectrum typically is very weak, the signals are very weak. So, to get reasonably good measurable signals, we use intense source, and lasers provide that kind of a source. So, lasers are preferred as a source of radiation for Raman spectroscopy. And if I want to make measurements in the UV region, typically what we do is we use electrical discharge sources, like typically a hydrogen lamp or a deuterium lamp. What you do is you have a evacuated glass chamber where the hydrogen or deuterium is there, and that is made to discharge. So, that gives out radiations in the UV region, and normally deuterium lamp is preferred over hydrogen lamp because the output is more intense, the radiant power is more for deuterium lamp. Similarly, for visible region, what do? We use tungsten filament lamp. That is a normal kind of a lamp that gives you radiation in the visible region, say about 370 nanometers to about 750, 760 nanometers. So, that is the whole range I get from visible lamp. So, having talked about radiation sources, now let us see, so as I mentioned earlier, our radiation sources are polychromatic. So, I need some kind of a mechanism to select appropriate wavelengths out of that. So, we need some kind of a device for that. Here again, the choice will depend on the region of the spectrum I am talking about. For example, if I want to talk about microwave region, in this case what happens is we normally do not need a monochromator, because the klystron which is used as a source of radiation itself gives you radiation in a very narrow range. So, you do not need any device to monochromatize it further. So, we can use it as such. And for IR region, there are two types of instrument we use. One are called as dispersive instruments. They employ grating monochromators. We talk about grating monochromators as we move further. And the modern instruments which are using FTIR based instruments, they will be used Michelson interferometer, which is slightly out of the scope of this session here. If we go further, for Raman spectrometry, as you said, we are using lasers, and we know the lasers are coherent monochromatic sources by themselves. So, here again we do not need to use any wavelength selector over there, because laser radiations are themselves monochromatic in nature. For UV visible spectrometry, we need variety of things here. So, one typically used is absorption filters, or second option we you have is called as monochromators. There again there are two types of monochromators, we will talk about that. Now, this wavelength selector is a very important device for any spectrometer. Let us learn the principle of different types of selectors used in the instruments here. Let us begin by talking about absorption filters. That are very simple things to do. What we do is typically an absorption filter will be some kind of a small piece of glass of a different colors. You must have seen that. Suppose white light is coming, I put a glass of a color, say blue color or yellow color, what I will see is a different color here. Okay. So, these kind of absorption filters, what they do is say I am talking about here, say white light, that white light can be created by suitably combining say an orange and blue color. So, suppose this is falling on this filter here. So, what will happen is this filter is such, this glass is such which will absorb say part of the radiation. So, the blue part of the radiation has been absorbed by this, and what comes out of it is the orange part. So, input is a broad based and output is a narrow range of the wavelengths over there. Okay. So, this is typically a kind of a absorption filters, but they are very crude instruments, crude components here, and that is why they are very cheap. They are used in the low cost instruments where the accuracy is not very important there. We have to have some idea about how things are, what kind of interactions happening there. So, in such instruments we use absorption filters. The problem with these absorption filters is that they do not provide monochromatic radiation, because they are very cheap, they are very crude. So, they give you a range, say from a very broad range you come to a narrow range, but you do not get one particular wavelength there. But what we can do is, if I use say a combination of filters, say I put one filter there, that white radiation is coming, say a very broad range is coming, this filter chops off a little of it, something smaller narrower comes there, I put another filter there, still narrow. So, I can use a combination of filters and try to get a relatively narrow band of wavelengths. That is possible here, but all said and done there are still very crude bit of components to be used in the measuring devices there. Now, monochromators which are used more often, rather they are employed, most of the instruments are employing monochromators there. As the name goes, monochromator, that means these are devices that can selectively provide radiation of a desired wavelength, a particular wavelength out of the whole range of wavelengths given by the source. And there are two types of monochromators we have. One are called as prism monochromators, as the name suggests we are using a prism in this case, and second one is we are using a grating. And let us see what is a prism monochromator. What is a prism monochromator is, they employ prism as a device which is going to give me a monochromatic radiation. What basically is done is that you have a prism, you pass the light here, and the light passes through that, I am sure that you all have seen that if white light is passed through prism, it gives you whole spectrum, that visible spectrum comes over there. So, that is coming because when the light passes through that, this white light is made up of all components there, VIBGYOR. Okay. So, the whole visible range is there, and these are of different wavelengths. When they pass through this prism, the glass prism has different refractive index for all these different wavelengths there. As a consequence, they get refracted to different extents. So, they get separated over there. So, that is made use of in creating a prism monochromator. So, as we know that the shorter wavelengths are refracted more than the longer wavelengths. Let us see how do we make use of it. What do we do here is, so we have some kind of a source here, somewhere here, maybe a tungsten lamp or maybe a deuterium lamp here, and then the radiation, the output from there is made to pass through some kind of a entrance slit. That means you chop off most of it and let the light go through it, use a kind of a lens and make the light pass through the prism. And when it passes the prism, it gets refracted, and the refracted light is again made to pass through a lens and made to focus on an exit slit. So, what we do here is we kind of rotate this prism. By rotating the prism, we are making different wavelengths of light pass on the exit slit, and this exit slit is the one which is going to take the radiation to the sample where the matter is contained over there. Okay. So, that is the basic principle of our prism monochromator, that is the prism is moved in such a fashion that different kind of wavelengths are coming out from the exit slit. So, that is how from a source which is polychromatic, I get radiation which are monochromatic in nature. Okay. So, that is how a prism monochromator works. The second kind of monochromators we have are called as based on the grating. I am sure that you have done at your school physics, you learnt about grating. Grating basically is a closely spaced parallel grooves. That means you take a smooth surface of a solid material and etch parallel grooves on that. Okay. So, when this radiation falls on that, that gets reflected by the grating, and the intensity of radiation reflected varies with the wavelength. That is the basic premise of a grating's work. The maximum, the wavelength which is having maximum intensity will depend on the angle at which the reflection is taking place. So, that is a device called as grating, and that is used to create a monochromator. What is done here is, so you have some kind of a source here, the radiation from the source are made to pass through a entrance slit, and from there they come onto a concave mirror, they get reflected and fall onto the grating here, and from there it gets reflected and fall on another mirror, and from there it is focused onto an exit slit here. So, here again what we do is, the input is coming here fine, that is the polychromatic radiation coming there, but what we do is we rotate this your grating here in such a fashion that different kinds of, when you rotate the grating in a predetermined way, it provides the output as a of a desired wavelength from the exit slit. That means, our input here is polychromatic, that is passing through the slit, falls on mirror, falls on the grating. I rotate the grating in such a fashion that the wavelengths which are coming out from here, they get altered. So, that means, at a given point of time I get only one particular wavelength coming out of the slit. So, I am getting a monochromatic output from a polychromatic input. Now, having talked about the radiation sources and the monochromators or the devices which are going to do wavelength selection. Now, the next step is, that means you had a source, you have got a monochromator, then next thing is you have to have some thing to hold our sample over there. So, how do we handle the sample, where do we load our sample, how do we keep the sample into the, how do we make the radiation and the matter interact. So, we have to have some kind of a means of holding the sample. Okay. So, what is done is, here again the basic premise of any sampling device is that the material used for holding the sample must be transparent to the types of EM radiations being used. For example, if I am talking, I am trying to do say microwave spectrum or IR spectrum or UV visible. So, whichever range I am talking about, I should use a material which is transparent to that range. Otherwise, what will happen is, if I suppose I use a glass material there and take my sample into a glass cuvette or a cell and make the radiation in IR region fall on that, IR will be absorbed by glass. So, I will not be able to study the interaction reasonably well. So, the material I am using for sample holder must be transparent to the type of EM radiation being used. So, that is the bottom line. So, our microwave spectroscopy, what we do is, typically the gaseous samples are taken into a evacuated waveguide using mica window. That means, you have got a long tubing which is evacuated, wherein you take the sample and both sides there are mica windows and the radiations will come from there. So, mica will be transparent to the microwave radiations there. In case of IR measurements, what we do is, typically IR measurements can be done with solid samples or with solutions and all. So, solid samples normally are used as mulls. That means, what you do is, you take some kind of a paraffin oil, put solid sample there, mix them together, make a mull, and that mull is put into some kind of a container which has got sodium chloride or potassium bromide windows. That means, you have a container and there are two windows on that. When the radiation falls on that, because I can't use glass here as I mentioned earlier. So, I have to use some material which is transparent to that, and typically sodium chloride or potassium bromide windows are used for the purpose. And another way of handling solid samples is that you take the solid sample, take a large amount of potassium bromide solid, mix the two together and kind of grind it well and press it into a transparent pellet. That means, you use some kind of a device of this kind, wherein evacuate and then try to grind, make a pellet which is transparent, and then this pellet can be put into the path of the radiation and the spectrum can be studied. Or maybe we can put this pellet into some other container which is again transparent to IR radiation. For handling aqueous samples, because many times what happens is, the sample which you want to study is soluble in water. If it is aqueous sample, I can't use say sodium chloride or potassium bromide windows, because they are water soluble. So, what do we do? In such cases, we will take recourse to the containers which are made up of silver chloride or calcium fluoride. They are typically used as containers. So, the samples will be held here, and then on both sides we will have some kind of a mechanism is there by which we can hold our liquid samples, and that samples can be put into the path of radiation and we can study the interaction. Going further, in case of Raman spectroscopy, things are slightly simpler. What we do is, if it is a liquid sample, we take it to a fine capillary and put it into the path of the radiation and see what is the consequence of that, how does the scattering take place. And if it is gaseous sample, what we do is, we think of a cuvette which is very long cylindrical glass tube which has got mirrors on both the sides, and on one of the sides the mirror has a hole. That means where the radiation will can come in, radiation passes through that and then gets reflected and gets absorbed, and then what you see is what is the consequence of that in terms of the scattering radiation which we try to measure from there. And as regards UV visible spectrometry, which is used most often because it is one of the common techniques used there, sample is typically taken in a quartz or a glass cuvette which is transparent to the wavelength of interest. And if I am talking about a UV visible UV range, typically quartz cuvettes are the most convenient one, and these cuvettes come in variety of shapes and sizes depending on how much is the volume you want to talk about, how much of volume you want to use, and what kind of container we have to keep there. So, they come in different shapes. They will be cylindrical or oval shaped, or maybe the variety of things. We can even vary temperature there. So, you can do number of things with the kind of cuvettes available with us. I mean the sample containers, but in terms of the construction material, they primarily are of quartz. But if I am trying to do study in the visible range, I can even use glass cuvettes. But glass cuvettes cannot be used in UV region because glass is going to absorb. Let us sum up what we have done today. What we have done today is that in this session we have tried to review what we talked about spectroscopy in the earlier sessions. Thereafter, we outlined the essential components of instruments for spectroscopy measurements, wherein we realized that for any spectroscopy measurement to be done, we had to have some kind of a source of radiation. Thereafter, I must have some device to kind of make some kind of a wavelength selection, because the source is always going to be a polychromatic source. From the polychromatic source, I need to have the selection of wavelengths of appropriate nature. So, for that I need a device called as a monochromator. Then thereafter, the radiation coming out of monochromator is to be put onto some kind of a sample holder, where the container where the sample is to be taken, and then output from there has to be detected by a detector, which has to be given for the signal output, which will be given as the spectral output, which I will be saying there. So, there are 5 essential components there, and they are arranged in an order I just talked about, but that is not that is a kind of a schematic way of looking at it, but this order gets altered in some of the cases, especially say in case of IR, etc. The sequence may be different. The monochromator may not come in the initial stage, it may come later. So, after having done that, what we have done, we have for each kind of spectroscopy which we are going to take up in this course, we have talked about the sources of radiation. Sources of radiation, say what do we do in case of microwave spectrometry, or what do we do in case of vibration spectrum measurement, that is in the IR region or UV visible region. So, we have seen what are sources used for different types of spectroscopies to be studied. Similarly, we talked about the types of wavelength selectors used, and primarily we know that the wavelength selectors are going to be the monochromators. We talked about 2 kinds of monochromators. One is a grating based monochromator or a prism based monochromator, or in visible spectrometers, the crude ones, we can even use simple glass filters over there. And towards the end, we talked about how do we handle, where do we keep the sample for the interactions to be studied. So, we talked about sample handling devices for a variety of spectroscopy studies we take up. In the next session, we will talk about that once the radiation has come after interaction with the sample, I have to have something to detect that. That detection devices, what are the detectors used in the spectrometric measurements, and then how do we take the output from the detector as a printout of a spectrum, or maybe we can see on a monitor, I can put into a computer and try